Today we will continue our discussion of operational amplifiers. In particular, we will discuss non-inverting and difference amplifiers with a review of inverting and summing amplifiers. At the end of today's lecture, a student should be able to define the different types of operational amplifiers, as well as apply KCL in order to determine the output voltage, the gain, current, or power of an op-amp. Remember to always assume that we will be using an ideal operational amplifier. Therefore, there will be two basic assumptions, including short circuit and infinite input impedance. And you will use KCL if you ever encounter an unfamiliar operational amplifier. Okay, let's get started. So in-class activity 1 states, design an operational amplifier circuit to find the average of three input voltages VA, VB, and VC. First, recall what average means. So, VO would be equal to VA plus VB plus VC divided by 3. The only operational amplifier that we've studied that has multiple inputs is a summing amplifier. So recall that the equation for a summing amplifier is VO is equal to negative RF over RA VA minus RF over RB VB minus RF over RC VC. That's negative, the sum, and remember it's a weighted sum. So in order to make it positive, we're going to do something we're going to talk about a little bit today, which is called a cascaded amplifier. So we're going to have the summing amplifier first, and then we're going to cascade that with an inverting amplifier. The purpose of the inverting amplifier is to make the sign positive instead of negative. So there are going to be three inputs, VA, VB, and VC. On the summing amplifier, they will all have a gain of 1. So we'll make all these resistors 1 kilo ohm. So the output of the first op-amp is negative VA minus VB minus VC. But I need to have a gain of 1/3 in order to find the average of the three inputs. So the feedback resistor on the inverting amplifier will be 1 kilo ohm, and the input resistor will be 3 kilo ohms. And so now my output would be 1/3 of VA plus VB plus VC. So now let's look at the formal definition of a cascaded operational amplifier. It is a head-to-tail arrangement of two or more op-amps such that the output of one is the input of the next one. When op-amp circuits are cascaded, each circuit is called a stage, and the overall gain for the cascaded op-amp is a product of the gain for each of the individual stages. So for example, if the overall gain was A, then the stage gains would be A1, A2, A3, and so on. So let's look at another example. Assume that the following op-amps are operating in a linear region, which means they're not in saturation, and we want to find the output VO. What is the numerical value of VO if V1 is 10 millivolts and V2 is 15 millivolts? So in order to solve this problem, our first task is to identify each of the operational amplifiers, and we would do this with block diagrams. Okay, so let's look at the top left op-amp first. This is actually a non-inverting amplifier. How do I know it's a non-inverting amplifier? I know it's a non-inverting amplifier because the input is at the positive terminal and the feedback resistor and the input resistor are at the negative terminal. So it's a non-inverting amplifier. The input is going to be V1, and in this box I'm going to put the gain. Remember, for a non-inverting amplifier, the gain is 1 plus RF over R1, where RF is 25 kilo ohms and R1 is 10 kilo ohms. So the gain for that one is 1 plus 25 over 10, which is 3.5. And I'll call the output of that op-amp VA. The bottom left op-amp is an inverting amplifier. How do I know it's an inverting amplifier? Well, the input is tied to the negative terminal through an input resistor that's 10K and a feedback resistor that's 50K. So the input is V2, and the gain is negative RF over RI, where RF is 50 kilo ohms and RI is 10 kilo ohms. So the gain is -5. And I'll call the output of that one VB. Both of these op amps feed into a summing amplifier. I know it's a summing amplifier because it's the only op amp I have that has multiple inputs. So this is going to be the summing. And the output is VO. Now they don't have the same gain. VA has a gain of 60K over 20K. Because remember, for a summing amplifier, the gains for each input are negative RF over the resistor at that input. So for VA, the gain is negative 60 over 20, or -3. For VB, the gain is negative 60 over 30, or -2. So if I write the equations for each of these stages, what I'm going to have is that VO is equal to -3 VA minus 2 VB. For the non-inverting, I would have that VA is equal to 3.5 V1. And for the inverting, VB is equal to -5 V2. So finally, VO is equal to -3 times 3.5 V1 minus 2 times -5 V2, which is equal to -10.5 V1 plus 10 V2. So now we'll put in the values of 10 millivolts and 15 millivolts, and we'll have -10.5 times 10 milli plus 10 times 15 milli, which makes the output 45 millivolts. Okay, now let's talk about the last type of op amps that we will discuss in this class. They're called difference amplifiers, and just like they sound, they're called difference amplifiers because you have an input on the positive terminal and the negative terminal, or the inverting and the non-inverting terminal. But once again, like a summing amplifier, it could be a weighted difference. If you look at that top right circuit, what you'll see here is that you could actually find the output of the difference amplifier by using superposition. And when you'll do that, you'll see that the terminal on the input on the negative terminal has a gain of -R2 over R1, like an inverting amplifier would, and the voltage on the positive terminal actually responds like a non-inverting amplifier, except it also has a voltage divider based upon R3 and R4. So those gains for the input would be -R2 over R1, and the gain for the output V2 would be R4 times R1 plus R2 over R1 times R3 plus R4. There are a couple of special cases. One of them is that if the ratio of R2 over R1 is equal to R4 over R3, then this difference amplifier becomes R2 over R1 times V2 minus V1. Now this is a pure difference amplifier because now when V2 equals V1, the output is actually 0. And if R2 over R1 is equal to R3 over R4, and those values are all the same resistance, this is purely a difference amplifier with no gain, V2 minus V1. Now let's look at a couple of examples of using cascaded amplifiers as well as the difference amplifier. The next couple of examples will look at two concepts, one of them being using difference, inverting, summing amplifiers, and also OpAmp design. What is OpAmp design? OpAmp design is when you're given an expression, such as an output, you want to determine what operational amplifier would implement that expression. The strategy for doing this is, number one, you identify the type of OpAmp you need. And number two, you identify the resistor values. So for in-class activity 3, we're going to design two different operational amplifier circuits to implement the expression VO equals 4.5 times VA minus VB. Now, since we have two inputs, we know our two choices. One is going to have to be a summing amplifier, and the other one would have to be a difference amplifier. Let's do the difference amplifier first, since that's what we just studied. So the first thing I'm going to do is to draw the difference amplifier, negative terminal and positive terminal, and I'm going to have the two inputs. So I'll draw the resistors for the two inputs. And here's VO. So if we have 4.5 times VA minus VB, VA is positive, so that goes on the positive terminal. VB has a negative coefficient, so that goes on the negative terminal. And the gain is 4.5 times VA minus VB. Since this is my example where both of the inputs have the same gain, I know that this is my bottom special case where the ratio of the feedback over the input should be 4.5. So I'll make the feedback resistor here 4.5 kilo ohms. I'll make the resistor tied to ground here 4.5 kilo ohms, and both of the input resistors would be 1 kilo ohm. So I've now designed an op-amp that has 4.5 times VA minus VB as an output. The other op-amp I designed is actually going to be, like I said, a summing amplifier. But remember, for a summing amplifier, both of the inputs have a negative gain. Since one of my inputs is actually positive here, I'm going to have to use an inverting amplifier as well. So what I'll draw first is an inverting amplifier with an input of VA. Why did I choose VA? Because VA is the one that has to be positive, so the sign will have to flip. This one is going to have a gain of 1 kilo ohm and 1 kilo ohm. So VA is the input to the inverting amplifier, and we want it to have a positive sign. So by going through the inverter first and then through the summer, VA will have a positive coefficient on the other side. And then on the output, we're going to have the summing amplifier, where one input is going to be now a negative VA, and the other input is going to be VB. So now, since I want the gain to be 4.5, the feedback resistor is going to be 4.5 kilo ohms, and the input resistor on both of them will be 1 kilo ohm. So this gives me VO is equal to 4.5 times VA minus VB. Okay, let's try another example. Design two different operational amplifier circuits to implement the expression VO equals 2VA minus 3VB. The first design should include two op-amps, and the second design should include one op-amp. For the two op-amp design, this is going to look an awful lot like the example we just did. So we're going to have an inverting amplifier with an input of VA, and it's once again going to be cascaded with a summing amplifier. So since the VA has a gain of 2, we will make the gain of the inverting 1, which makes VA negative VA coming at the output of the inverting amplifier. And we'll make the other input VB, and to get a gain of 2, we will have a feedback resistor that will give me a gain of 2, but also give me a gain of 3 for VB. So I'll pick something that's at least common multiple of 2 and 3, and we'll do 6 kilo ohms. So if I make the feedback resistor 6 kilo ohms, and I want a gain of 2 for VA, I make the input resistor 3 kilo ohms. And for VB to have a gain of 3, I make the input resistor on VB 2 kilo ohms, and this gives me an output of 2 VA minus 3 VB. Okay, so now for part B, we're going to use a difference amplifier. So first I'll draw the op-amp. Here's the positive terminal, the negative terminal, the input resistors, and the feedback resistor. Since VA is positive, VA will be on the positive terminal, and VB will be on the negative terminal. I'll label the resistor values R1, R2, R3, and R4. So now, if VO is equal to 2 VA minus 3 VB, then this is equal to R4 over R1 times R1 plus R2 over R3 plus R4 times VA minus R2 over R1 VB. So it's easier to do R2 over R1 first because R2 over R1 has to be equal to 3. So we'll let R2 equal 3 kilo ohms and R1 equal 1 kilo ohm. Notice any values for R2 and R1 that satisfy that ratio are acceptable. We typically select resistor values to be in the kilo ohm range in order to not draw too much current into the op amp or saturate too much power, and also too large of resistors could be noisy. So we keep the resistors in the kilo ohm range. So I'll put on the circuit R2 is 3 kilo ohms and R1 is 1 kilo ohm. So now I know the coefficient on VA has to be a 2. So I'm going to set this expression equal to 2, but put in the values that I have selected for R1 and R2. So I'm going to have R4 over 1 times 4 over R3 plus R4, and that has to equal 2. And you can solve this equation for the ratio R3 equals R4. So as long as I pick values where R3 and R4 are equal, this will satisfy that expression. So we're going to let R3 equal R4 equal 1 kilo ohm. So I'll put 1 kilo ohm on the circuit for each one of those resistors. And we have now designed a difference amplifier to implement the expression 2 VA minus 3 VB. Okay, now let's do the last set of examples for today's lecture. Here we have a weighted difference amplifier with VA equal to 100 millivolts. What range of values for VB will result in linear operation? What you should notice here is that the rails are negative and positive 12 volts. So what this question is really asking is, what value of VB will keep the output between negative and positive 12 volts? Let's actually find the output first. So remember, VO is equal to R4 over R1 times the quantity R1 plus R2 divided by the quantity R3 plus R4 times VB minus R2 over R1 VA. So if you put in the numeric values for all of those resistors, knowing that the 20K resistor is R1, the 1 meg resistor is R2, the 8K resistor is R3, and the 2K resistor is R4, what you end up with is that VO is equal to 10.2 VB minus 50 VA. So I'll put this in my inequality, and I'll have 10.2 VB minus 50 VA must be between negative 12 and positive 12. So if VA is equal to 100 millivolts, then this becomes negative 12 is less than or equal to 10.2 VB minus 5, which is less than or equal to 12. I'll solve this inequality for VB, and that yields that for linear operation, VB must be between negative 0.686 and positive 1.67 volts. Okay, let's do one final example using the same circuit from above. If VA is equal to 100 millivolts, what value of VB results in an output voltage of 10 volts? So we'll use the same equation. VO is equal to 10.2 VB minus 50 VA, but we will substitute in 100 millivolts for VA. So we'll have VO equals 10.2 VB minus 5, and we want this to be 10. So 10 is equal to 10.2 VB minus 5, or 15 is equal to 10.2 VB. And finally, we solve for VB. So VB must be equal to 1.47 volts. This concludes today's lecture on difference amplifiers, cascaded amplifiers, and our review of non-inverting, inverting, and summing amplifiers.